We're going to solve this dynamic optimization problem to minimize the integral of x1 squared from 0 to time final. In this case, time final is going to be 1.5. We're subject to, so ST means subject to, the following conditions or the equations. We have two differential equations, or the derivative with respect to time of x1 equals u plus x2. And the derivative of x2 is equal to negative u. The thing that we can adjust in this problem is the value of u. So that's why we put it underneath the min sign. It means that that becomes the degree of freedom, or we can adjust the value of u at every time point in this horizon between 0 and time final. So we have a couple initial conditions here. x0 is these are the initial conditions, so this would be the initial condition for x1 and for x2 at time 0. Okay, so the next one is that our final conditions, so both of these have to be equal to, at the final time it has to be equal to 0 for x1 and x2. Okay, so this is where they start, and this is where it's going to finish, and we want to try to minimize this objective function along the way. So we know the starting and ending point, but the path on how we get there is going to be how what we'll use u to determine how we get there. We have some constraints on u, an upper bound. Okay, so this is our upper bound for u is 1, and then our lower bound is going to be a -1. So let's just set this up and solve it. I'm going to just open up a new text document, and we'll name this one this will be our model file. This is a Bryson dynamic optimization problem. It's a classic problem that's been reported and solved as a benchmark case. Okay, so I have some parameters here. I'm going to have p. This is going to be an extra one just to minimize at the very final point this objective function. Then I have my u value. I'm going to set that, just give it a guess value of 0, a lower bound of -1, and an upper bound of 1. The commas there are optional. We have some variables, x1 and then x2. It can either be 1 or 0. We'll show that, first of all, a value of 1 there is going to give us an infeasible solution, and then we'll change it to 0 to solve it make it feasible. Okay, so equations will minimize our objective function. I'll multiply that by 0.5 as well, and then also multiply by this p parameter, which means I'm going to have p be 0 everywhere except at the very last point. Okay, the derivative of my objective is equal to x1 squared. So what I've done is I've just translated this part of it right here, okay, into, I just said that that equals my objective. Okay, let me rewrite that. Okay, so that equals my objective, and I just differentiated both sides. So the derivative of my objective with respect to time then just equals x1 squared. And I could put that 0.5 in there as well. Okay, that one isn't really going to make a difference in this case if I have the 0.5 in there or not. Okay, so this is the equation that I'm actually putting into my model to be able to solve for the objective. Okay, to integrate the objective. And then I have these two additional differential equations for x1 and x2. And I have some 0 point endpoint constraints, so I'm just going to multiply this p parameter times x1, set that equal to 0, and do the same thing for x2. Okay, so here's my model file that's going to describe this optimization problem. Now I need to set up a data file as well. I'll just do this in Excel. I'll have some time values. I'm going to give it just an initial, very short time interval so it can make a decision on U. It's going to start with 0 just because I put that in as an initial condition, but I want it to, within 1,000th of a time unit, to decide a new U value. Then I'm going to go by increments of 0.02. Okay, and then let's go up to 1.5, and then on the p-value, this is going to be 0 everywhere, and then just at the very end, I'm going to set that equal to 1. Okay, so there is my my data file. When you save it, it's going to ask if you want to save it in the CSV file format. You want to select that comma separated value file, and I'm going to select yes. I'll go ahead and keep it in that form. Okay, and then the last thing that I want to do is create a Python or Matlab script. I'll go ahead and show both of them, but this is going to then take our model and data file and then solve them, and then we'll also show the solution and plot the results. Okay, so in Matlab we'll just clear all, define the server, and then application name. I'll add path to this APM folder. I'll show you where you can download these files with the APM folder. And then we'll clear all, load the model file, load the data file. Okay, so in Python, very similar, server application name. We'll just import APM. This is going to be an APM module or add-on. We'll clear all, load the model file, load the data file. Okay, so very similar between the two. I'm going to have a couple options here. I'm going to set the nodes equal to 2 and the solver is equal to 3. Nodes is the number of collocation intervals for each time step. And NLC solver, that is the that's the nonlinear control solver. That's going to be IPOpt is number 3. Okay, default is number 1, which is the APOpt solver. Okay, same thing here for those options in Python. And then I also have iMode 6, that's dynamic optimization, and I'll set that here as well. MB type is 1, that just means a first order hold between time collocation intervals, instead of a 0 order hold, which would be 0 for that option. Okay, I'm going to set up my first manipulated variable. Okay, I use the APM info to do that. This allows me to turn on the degree of freedom from the script. So status of 1, and then I'm going to put a small delta cost on it. I like to do that just to, you know, especially for these singular control problems, if there's no reason to move the value of U, then this small delta cost penalty will prevent it from moving. Okay, and then I'm going to solve it. Okay, so this is all I need to do to set up and solve it. Essentially what I'm doing is just loading my model file, loading my data file, setting a couple options, setting up my degree of freedom or manipulated variable, and then solving it. Okay, so now it's just retrieving the solution and plotting it. So I'm going to display the output of the solver and retrieve the solution. And here I'll just print the output. If you're in Python 3.3 plus, you just need to put the parentheses there on the print, and that so this is 2.7 here for Python. Okay, so I'm then just going to display the optimal solution, just get the very end value of this objective function. This should actually be multiplied by 0.5, but it's about the same. Okay, so it'll give you the same answer either way. It'll just report the objective function slightly differently. Okay, let's go ahead and create our first figure. I'm going to just plot x1. You got to hold on to that plot so you can plot additional things. I'll plot x2 and the value of u. Change the line width there to just make it a little bit thicker. Set it equal to 2 versus the default of 1. And then put a legend there with x1, x2, and u. And then y label, x label, and then change the axis a little bit. Okay, so I'm going to import matplotlib in Python, and then basically have very similar, x1, x2, and u, and then plot the legend, y label, x label, and axis, and then just show the plot. Okay, so let's solve this now. I'm going to open it up in Matlab, and then also open it in Python. This one I'll just do in IDLE. You can do it in Spider or some other environment as well. Okay, and then I'll just run run the module, and you'll see that it gave an error code, that there were some infeasibilities. Okay, so it started, this x2 value started at 1, but the solver said, there's Matlab that just opened. Okay, so the solver said, well, there's no solution to that. So the solver actually moved it down here closer to 0, and then it was able to get, satisfy the final constraints of equal to 0. And so there's obviously an infeasibility here. It reported it as infeasible. We can use the APM get infeasibilities.txt. So let's go ahead and just put that into our script just to be able to get a report of which equations might be infeasible. So I'm just going to change the server. I named that S, and the application I named A. So it's going to retrieve infeasibilities.txt. Okay, I'll go ahead and save it and then run it. Let me go ahead and close this plot and then run it again. Okay, so it ran it again, generated an infeasibilities.txt file, and should have put it right here, okay, in my folder. If I open that up, let's see, reload it, yes. Okay, so here's my infeasibilities report, and it said that I couldn't solve, okay, I couldn't solve this particular equation. Okay, so let's just look at this. We have possible infeasible equations, and it is the in this case it's the collocation, it's the derivative value, but you can see some of the variables and the values and their upper and lower values. So this is the equation that it couldn't solve. Okay, so let's do this then. We're going to then come back here. Let me minimize this, and let's just change our initial condition. Okay, we're going to change our initial condition to, okay, I need to grab this again. Okay, so we're going to change our initial condition to, instead of 1, we'll change it to 0, and then solve it again. Okay, so I've got, let me go back to my Python, and then run, and then, so that was just error from not closing the plot beforehand. Okay, so now I can see the solution. Here's my value of u, and then it dropped to about -0.2, and then to -1. Okay, so this gave me a feasible, it says optimal solution found, it was feasible, and there's my objective, and I'd have to multiply that by 0.5 to get the objective that's found in the problem statement. Okay, so there's the solution to this problem. And then let's solve it in Matlab as well. Here's the same script, and if I just run it, it should give me the same answer that the other one gave. Okay, so I'm going to come back here. This is the IPOpt iteration summary. Okay, you see you have some negative degrees of freedom here, but a lot of those equations were not active. That p times x1 and p times x2, those were not active. Because it's just 0 equals 0 there for most of the time points, and so it didn't really have a problem with that. It was able to find this optimal solution. Okay, and then let's just look at the Matlab plot there. So same answer that we got in Python, but this one is in Matlab instead. Okay, so let's just go back to the problem statement, make sure that we've answered everything here. This problem says to report the optimal objective value and display a plot of relevant variables for x1, x2, and u. So just note that this problem has initial conditions for x1 and x2 as well as final conditions that must be satisfied, and it's the integral of the objective, not just the final value that must be minimized by adjusting the value of u, and then ensure that any solution has sufficient grid points to accurately represent the system dynamics and objective. Okay, so for this very last one, this is called a grid independence study, and so what you can do is come into your Excel file, okay, your CSV file, and then one of the things I like to do is double or have the time steps, and then see if the solution is going to change. Okay, so instead of 0.02, let's go 0.04 with the time steps, and I'm just going to fill that down to let's go down to 1.5. Okay, and then I'm going to delete all the rest of these, put a 1 there for my p-value, and let's just see if the solution is going to change with larger time steps. Okay, so I'm going to come back to, I'll just do this in Python, run it again. I'll have an objective function. You can see that right here that the solution did change a little bit. Okay, and so what you can do is come back in here and change the delta t on the time until the solution stops changing. So that's called a grid independence study. There's some more recent work that's come out lately on optimizing those collocation intervals, but just a very simple way to do it would be to just change your delta t here in the data file until the solution stops changing. Okay, and then you've gotten rid of discretization errors. Okay, so that concludes this problem on setting up and solving this dynamic optimization problem.